Welcome to the next session. In the previous session, we have discussed up to the question number 43. So, in the quality parameters of water topic, we are doing the previous questions. So, let us continue it. So, question number 44. It is GATE 1993 1 mark question. Bacterial examination of drinking water for Escherichia coliforms E. coli is performed because option A is they are pathogenic, causing intestinal diseases, which is wrong. They are not pathogenic. Option B is their presence indicates viral contamination of water. Okay. Option C is they are used as indicator organisms for probable presence of pathogens. Option C. And option D, they represent unique indicator organism for sewage pollution. So option B and D are not relevant. Option C is more relevant. So E. coli bacteria indicates E. coli is a non-pathogenic bacteria belongs to coliform group, The presence of E. coli indicates the presence of E. coli indicates the presence of pathogenic bacteria. Indicates pathogens, or it may be pathogenic bacteria also, that is B. coli. Okay, so this is the solution for question number 44. Question number 45. Question number 45 is GATE 1996 1 mark question. 1996 1 mark question. So the question is the most important water quality parameter for domestic use of water. So there are 4 options given. One is carbonate hardness, and B is non-carbonate hardness, and C is coliform group of organisms, that is pathogens, and D is chlorides. Among these 4, which one is more important water quality parameter? Let us see. So these both comes under hardness. Hardness is having a limit, should not be more than 200 and it should not be more than 600 in alternative source is not available. Okay. So this is the limit of this. Chloride also the limit is 250 mg per liter and it should not be more than 1000 mg per liter. And whereas the limit for this third option is nil. It should not be present at all. So now tell me which is important. So where we don't at all accept its presence in the water, that should be the important quality parameter. Because if it present also, it is not harmful to some extent. If chlorides present also, they are not harmful to some extent. But we cannot at all allow these pathogens. That is why this is the most important water quality parameter from the given options. Okay. from the given options. So question number 46, 1997, 1 mark. (1997) 1 mark. MPN index is a measure of one of the following. MPN index. See, MPN index, most probable number index, is a measure of what? Is a measure of coliform bacteria. Coliform bacteria, that is the answer. The first option is the answer. Is a measure of coliform bacteria. Very simple question this is. 1998, 47, 1998, 1 mark. Excuse me. 1998, 1 mark. Question number 47. So the question is, the microbial quantity of treated piped water supplies is monitored by. So microbial quality is nothing but microorganisms presence. Option A is microscopic examination. Option B is plate count of heterotrophic bacteria, and option C is coliform MPN test. Option D, identification of all pathogens. So we don't identify all the pathogens, we identify only E. coli, and we assume that if E. coli is present, that means all other pathogens are also present. That is why we do coliform MPN test. Okay. Microbial quality of water is ascertained by, is monitored by MPN test. Is monitored by most probable number test, coliform MPN test. Okay. So next question, 48th question. 48, 2004, 1 mark question. So the question is, hardness of water is directly measured by titration with ethylene diamine tetraacetic acid EDTA using what indicator? It's a very simple question. Erythrome black tea. EBT is the answer. EBT is the answer. Okay. Erythrome black tea is the answer. 49. The organism which exhibits. It is also GATE 2004 1 mark question. Question number 49. The organism which exhibits very nearly the characteristic of an ideal pathogenic indicator is Escherichia coli, E. coli. So 49, it is E. coli. E. coli is the answer. It is also very simple question. No need to explain much. So 50th question. It is GATE 2004 2 marks question. GATE 2004 last question. Question 50. 2 marks question. The question is like this: a standard multiple tube fermentation test was conducted on a sample of water from a surface stream. The results of the analysis for the confirmed test are given below. Sample size So this is test dilution. Sample size in ml. Sample size in ml 1, 0.1, 0.01. And here number of positive out of 5 tubes. Here number of negative out of 5 tubes. Okay, so it is 431. So obviously if there are 4 positives, obviously there will be 1 negative, 3 plus 2, 1 plus 4. So these are the negative tubes. Okay, now this is test dilution. This is test dilution. So to meet this test dilution, table dilution was also given. So MPN index of 95% confidence limit for the positive results when 5 tubes used for dilutions is given like this. This is table dilution. Table dilution with 10 ml, 1 ml, 0.1 ml. With these dilutions, the chart combination of positive, combination of positive 4, 3, 1, combination of positive 4, 3, 4, 2, 1, 4, 2, 1. MPN index per 100 ml. MPN index per 100 ml, it was given as 26. It is given as 26 here. Okay, so 95% confidence limit, 95% confidence limit, lower, upper. It is lower value was given as 12, upper value is 65. Okay, similarly another combination 431, another combination 431, here it is 33, 15, 77, 15 and 77. Okay, so here what is the lower limits, upper limits, confidence limit is these things are not at all needed to understand. Okay, it is just extra information which is not needed. So during examination we think much about all these things and we simply leave the questions thinking that it was given something else which we haven't discussed in the class and all. Never think like that. Whatever the concepts we have discussed are completely sufficient for the GATE examination, completely sufficient for the GATE examination. In very few instances only we will get a new model that is new to everyone, because everybody will study the same concepts. Okay, so whatever the concepts are 100% sufficient. So that is why don't ever think that if this is not discussed in the class, that means it is not needed. Okay, so only thing here we need to do is, see, this is test dilution, this is table dilution. Okay, this is test dilution and this is table dilution. I told you already. See here for 1 ml for 10 ml the value is 4. We need to compare it here. So here we got the positive as 431. So this is the test dilution positives. We need to take the data from the corresponding to this positive values from the table. So from the table, this positive is matching with this positive. So we need to take from the table where you are getting the same combination, So this is the MPN number I need to take. But here, so the dilutions were 10, 1 and 0.1. But here the dilution is 1, 0.1 and 0.01. I told you already in the previous session. So if 1 ml is getting 4 positives, that means the concentration of the bacteria is more here. The concentration of bacteria is more here. Okay, so that is the MPN of test dilution. MPN of test dilution is equal to MPN of table dilution. MPN of table dilution into table dilution by test dilution. Table dilution by test dilution. So that means table dilution for the 431 combination. What is the table dilution's MPN? It is 33. So what is table dilutions? Any value you can take, but corresponding value you need to take. I am taking here 10 and corresponding value is 1 here. So 10 and 1 I am taking. So table dilution value is 10, corresponding test dilution value is 1. So the MPN number is 330 numbers per 100 ml. 330 numbers per 100 ml. That is the answer. Okay, so here we didn't use this confidence limits, anything we haven't used, but only it is given just to confuse us. Okay, so this is all about the quality characteristics of the water, and all the previous GATE examinations question up to 2019 we have did. Okay, we have did up to 2019. So let us go to the next topic of this subject, that is treatment. So now what we have did is we have ascertained all the qualities of the water and whether the qualities are as per the requirements of IS code or not. Everything we have determined. Now what we will do is we will start our treatment process. So how to treat the water, treatment of water. Let us see. Treatment of water. See, treatment of water contains various stages. Various components will come in the treatment, ranging starting from screening to the ending at miscellaneous treatments. So what are the different kinds of treatments we are having? Screening, and after that we do aeration, screening, aeration, sedimentation, plain and with coagulant. We do sedimentation, either plain sedimentation or with coagulant, using coagulant or aided sedimentation. After that, filtration, after that disinfection, after disinfection we apply miscellaneous water treatments such as removal of hardness, fluorine, salts, etc. There are many miscellaneous water treatments. So we do all these things separately because they are not present in every water. So they are present only for a particular region, for a particular kind of water. That is why these miscellaneous water treatment we discuss separately. But most of the water will have all these impurities present. So these treatments are common to every water which is present everywhere. So that is why we discuss only these parts. Okay, we will discuss one by one. This is one chapter, this is one chapter, this is one chapter, that is one chapter. Everything is one chapter in this. After this miscellaneous water treatments, and we will send the water to the distribution network. Okay, we will send the water to the distribution network. Now see, generally if it is groundwater, generally there is a difference in the treatment for groundwater as well as surface water. So surface water contains more suspended impurity than dissolved impurity. Because dissolved impurities means what? The metallic ions, dissolved gases, or non-metallic ions also. So all these ionic forms that will be dissolved in water. Okay, they will react with water and they will be in dissolved form in water. So whenever the surface water will get interaction with the environment, surface water is exposed to the environment, because of which these dissolved impurities, okay, these dissolved impurities will get neutralized. Okay, will get neutralized. So when they get neutralized, for example, CO2 minus is a dissolved impurity in water like H2CO3. It is present in the form of an acid in water. Now, if calcium is present in the nature anywhere, then this CO3 2 minus will react with calcium and it will become calcium carbonate precipitate. It will become calcium carbonate precipitate. Similarly, iron ion is present in water, so it will find some OH minus ion anywhere, so it will become FuOH thrice precipitate. So likewise, so the dissolved impurities, when they get the oppositely charged compound, they will react with that and they will form precipitate. Once they form precipitate, there are no more dissolved impurities. Now they have become suspended impurity, because see, this thing happens only in surface waters. So for this to happen, it needs environmental interaction. So only by having that environmental interaction, it will get the suitable ions, okay, so that it can neutralize on its own. So that is why in surface water, more suspended impurity will present than dissolved impurity. That is one thing. If you go for groundwater contains more dissolved impurity than suspended impurity. Because here how the groundwater is generating. So the surface water will pass through the earth surfaces, the layers of earth, and it meets the groundwater table. So that means during its path, during its travel, so it has to pass through the pores of the soil, which acts like a filter media, because of which all the suspended impurity which is present in the water gets removed by this earth filter bed. So that is why if the suspended impurities can be removed by that filter media, but the dissolved impurities will remain with that water and reaches the groundwater, and groundwater does not have any kind of interaction with the environment as surface water is having, because groundwater is completely covered with earth. So that is why, because of a non-interaction with the environment, the dissolved gases and dissolved ions will remain in the groundwater. Dissolved gases and dissolved ions will remain in the groundwater. That is why if you are taking groundwater, we have no need of screening, we need aeration, because by aeration only the environmental interaction you are artificially creating with to the water. So this aeration is needed for dissolved, this aeration is needed for groundwater, whereas this aeration is not needed for surface water. Screening is needed for surface water, but screening is not needed for groundwater. Sedimentation is needed for surface water, sedimentation is not needed for plain sedimentation. Plain sedimentation is needed for surface water, but plain sedimentation is not needed for groundwater. Sedimentation aided with coagulation is needed for groundwater, because this coagulant is effective in removal of dissolved ions and colloidal particles, dissolved impurities and colloidal particles. To remove those colloidal and dissolved particles, coagulant will be more effective than simple plain sedimentation. So that is why this coagulation or aided sedimentation we perform for groundwater, whereas for surface water plain sedimentation is better. Again, filtration disinfection is common for both kinds of water. So the thing is, so surface water need different kinds of treatments, groundwater need different kinds of treatment, that we need to know, that we need to understand it. Okay, that is why I have explained I have made the differentiations. Now there are two things again. All the treatment processes are classified into two kinds, that is unit operations and unit processes. What is unit operation and what is unit process? Let us see. Unit operation and unit process. See, unit operation means, so when you remove any kind of impurity by physical forces, when you removal of impurities by physical forces, see, such as screening. If you look at screening, we are using mechanical strainers. We are straining the particles on the screen, and by that force we are removing the particles, impurities, suspended impurities in the water. Similarly, if you go for plain sedimentation, in plain sedimentation the particle is allowed to settle down in the sedimentation tank upon its self weight. So weight force is acting. So that means by some kind of physical forces, if you are removing the impurities present in the water, that is called unit operation. Examples I told you right now: screening, plain sedimentation, filtration. So these are some kinds of unit operations examples. Whereas unit process means impurities are removed by chemical processes. Okay, removal of impurities by chemical means. So for example, if you see coagulant, so the coagulant will react with the colloidal particles and it forms a flock. So there is some chemical equations, chemistry is involved in the formation of flock. So that is why it is removed by the means of chemical forces or chemical means. Okay. So if you look at chlorination, again chlorine is also a kind of a chemical which reacts with the metallic ions, which reacts with the microorganism, and it forms some kind of reactions. Okay, that is why it is also removing the impurities by chemical means. Okay, so these kind of removal processes by which we are using some kind of chemicals, then it is called chemical removal. So that is nothing but unit process. Unit process is chemical removal. Example is coagulation and chlorination, removal of hardness, etc. So these are all chemical unit processes where we use chemical means to remove the impurity. Okay, chemical processes we are involved in this. Now, so let us see. The first one, screening. We will look into now different kinds of treatment processes. We will discuss one by one. Let us start with screens. Let us start with screen. So screening, screening is also called a trash rack. We also call it as trash rack. So generally different kinds of screens are there depending upon the dimensions of the aperture. Dimensions of the aperture, there are two types. One is coarse screen and second one is fine screen. So screen is of two types. So one is coarse screen and another one is fine screen. So the coarse screen will have a aperture dimension of 20 to 100 mm spacing. 20 to 100 mm center to center spacing, and fine screen, it will be having a spacing of less than 10 mm, less than 10 mm. So generally we use this coarse screen. Coarse screen is also called bar screen or trash rack. Bar screen or trash rack. Okay, so generally we place this screens little inclined. We place the screens little inclined. Why? Because in order to allow the flow, smoothly, okay, so that the velocity will reduces when you apply, when you keep this screen inclined to the water flow. So for example, if you keep the screen like this, then what happens? Whatever the water that is coming onto the screen will recedes. It acts like a sedimentation tank also. If you keep it with some inclination, if you are keeping this inclination opposite to the flow, then it will increase the flow. It is attacking mode. So this is accepting mode. If you are keeping the inclination in the direction of the flow, then it is accepting mode. Okay. So that is why generally we keep it inclined. Okay. Now here whatever the inflow which is entering onto the screen will move out of the screen also. Okay, the inflow is coming onto the screen is equal to the outflow. So but there will be small head loss will be present because it is passing through the screen. So there will be small head loss in the outflow. Okay, so this is head loss. This is head loss, and this head loss is equal to K into Vs square minus Va square, K into Vs square by Va square by 2G. Okay, Vs is velocity through the screen. That means Vs is the velocity on the downstream side. Here the velocity is Vs, here the velocity is Va. Va is approach velocity, and Vs is velocity of screen, velocity through screen. Velocity through the screen. So generally the cross-sectional area required for the flow, cross-sectional area is equal to what? So the approach velocity. So if Q in is the inflow, Va is the approach velocity. So the cross-sectional area of screen is equal to Q inflow by approach velocity. So this is the cross-sectional area of the screen that is needed, cross-sectional area of the screen that is needed, where A is equal to, so this is the side view of the screen. If you look at the front view, then it should be like a bars, like a mesh. Okay, if you look at a mesh, how it looks, similarly it looks like a mesh. Okay, it looks like a mesh. Now if it looks like a mesh, how it will be? So here it will look like this. From the front view it looks like this. There won't be any horizontal bars, only vertical bars will be present. Okay, so this is B. If I take this as B, so B into H, if I take this as H, so B into H, so B into H is the cross-sectional area of the screen, and this B into H should be equal to, so B into H should be equal to, so here cross sections it constitutes of bars and spacings. B into H, so B is nothing but what is B? So this is spacing. Okay, so spacing 1, 2, 3, 4, 5, 6, 7 spacings are there. 7 spacings are there for how many bars? 1, 2, 3, 4, 5, 6, 7, 8 bars. So when n spacings are there, there will be n plus 1 bars. So bar will have a diameter. So ns is the spacing and phi is the diameter of the bar. So B is equal to n plus 1 times of phi and n times of spacing. Okay, so into H. This is the cross-sectional area. This is the, if you know the spacing and if you know the diameter of the bar, then also we can find the cross-sectional area. Okay, and also generally for general cases, spacing we keep as 25 mm. General cases for general cases, spacing we keep it as 25 mm and phi we keep it as 10 mm. We take phi as 10 mm and spacing as 25 mm. Okay, spacing as 25 mm. So here, how to find the screen velocity, velocity of the water through the screen. Okay, velocity of water through the screen, Vs, velocity of water through the screen. Velocity of water through the screen, that is VA. VA is equal to, so whatever the flow that is going out, Q in or Q out, both are same, Q by aperture area. Q by aperture area. So what is the aperture area? What is the aperture area? Aperture area means, so if the screen is inclined like this, so if the screen is inclined like this, so the dimension, actually this is h, but this is not h, as the h is inclined, so this value is little more than h. This value is little more than h. And we know the inclination of the, inclination of the screen. Generally, this is theta. We keep it at 1 horizontal, varies with 3 to 6 vertical. Okay. So generally the slope we keep it as 1 horizontal, 3 to 6 vertical. So we know the theta here. So if we know the theta here, then sin theta is equal to h by y. That means y is equal to h by sin theta. Okay. So the aperture area is equal to b multiplied with y. So that is b into h by sin theta. B into h by sin theta. So the aperture means openings. So when you are taking openings, then the value of b is n into s only. We don't consider the bars. So we only consider the openings. So n into s, this is b, which is aperture, into h by sin theta. So the screening velocity Vs is equal to, so velocity of water through screens is equal to Q by n into spacing s into h by sin theta. Okay, Q by n into s into h by sin theta. This is the velocity of water through the screens. Okay, so likewise we will design the screens. So this is all about screening. So we will discuss the sedimentation topic in the next session. Thank you so much.